The early and canonical approaches to machine learning all involve providing expert labels on the data. We call that supervised learning. Most of what we've been doing so far has been supervised learning. But wouldn't it be great if a machine learner could figure out the data for itself and somehow be made to work with less supervision? The similarity-based algorithms we've seen have already given us ideas about providing less supervision. Let's think of it this way. Let's say we have two data points that are very close, but only one is labeled. The algorithm could go out on a limb and label the second instance. In this lesson, we'll talk about how we can create semi-supervised learning algorithms that benefit from a combination of supervised and unsupervised examples. Let's do a thought experiment. Imagine we have a set of data points in 2 dimensions. The data is unsupervised. We have no labels. But using what we know about the similarity or nearness of points in the space, we might think of the points as falling into 3 clusters. We don't know what the labels the points have, but we might guess that within each of these clusters, points share the same label. That's reminiscent of what happens in a nearest neighbor classifier or a support vector machine. Unlabeled instances get their labels from nearby labeled instances. Now, imagine that we get a very small number of labels, just 2 per class on average. The labels go to whichever cluster they happen to fall into. The analysis that we did on the unsupervised points suggests that we can label remaining points consistently within each cluster. This approach, unsupervised clustering, followed by diffusing any known labels to other points within the cluster, is an example of a semi-supervised learning algorithm. The unsupervised clustering step depends on being able to assess nearness. In this 2-dimensional case, straight line distance, also known as Euclidean distance, is a very natural choice. In this approach to semi-supervised learning, the supervised part is a very easy computation. To apply the supervision, the approach just diffuses labels to other instances in the same cluster. The clustering part is where the machine learning action is. Let's take a closer look at clustering to understand what is possible and how we can find good clusters automatically. First of all, what kind of behavior do we want from a good clustering algorithm? Up until the 21st century, there had been a lot of vaguely competing ideas about what a clustering algorithm should do, but little work on formulating a precise problem definition. In 2002, John Kleinberg, a theoretical computer scientist at Cornell, analyzed clustering, and his perspective helped introduce some clarity about what clustering might mean and how to set realistic expectations about what it can do. Returning to our simple example, the clusters that we see in a picture remain the same even if we zoom in or out. An algorithm that violates this rule would, for example, merge clusters as we zoom out. John Kleinberg called the property of clusterings remaining the same before and after a zoom operation scale invariance. This property is the first of 3 properties that make for a good clustering algorithm. A second and related property is that a clustering algorithm should remain consistent if the individual clusters are compressed or the distance between clusters is stretched. If the clustering algorithm clusters a set of data in a particular way, it should continue to do so if the within cluster distances decrease and the between cluster distances increase. That is, if the clustering algorithm likes a clustering, it should also like it if the set of clusters becomes more spread out and each individual cluster becomes more compact. Kleinberg called this property consistency. A third desirable property in Kleinberg's analysis is richness, where no conceivable way of clustering is entirely forbidden. That is, the algorithm's choice of clustering should range from each item being in its own cluster to every point clumped together into a big single cluster to everything in between. Nothing is ruled out beforehand. In its simplest form, richness has 2 aspects. There must be some arrangement of the points that makes the clustering algorithm put every point into its own cluster, and there must be some other arrangement of the points that makes the clustering algorithm group some points together. With these 3 properties in mind, let's look at a few candidate clustering algorithms. First, what happens if we have a clustering algorithm with a fixed distance threshold, say 0.1? This choice puts points in the same cluster whenever they are closer than that fixed threshold. This algorithm provides consistency. If within cluster distances are already below the distance threshold, shrinking those distances won't make them rise above the threshold. And if the between cluster distances are above the distance threshold, expanding those distances won't make them smaller than the threshold. The algorithm also provides richness. If we want the clustering algorithm to cluster the points all separately, we just have to place the points far enough apart. If we want the clustering algorithm to cluster some points together, we just need to put some points closer than the fixed threshold. But the distance threshold approach does not provide scale invariance. If we zoom in enough by increasing all the distances by a fixed ratio, points break off to form new clusters. The problem, of course, is that a fixed distance threshold of 0.1 didn't scale up with the spacing between the points. Let's consider an algorithm that chooses a threshold dynamically by scaling it to be the fixed percentage of the largest distance between points. As the distances are scaled up or down, the clustering will remain the same. This approach does provide scale invariance. This algorithm has the property of richness too, as we can space the points out so they form clusters or not. But this ratio threshold algorithm lacks the consistency property. As we spread out the clusters, the threshold grows and can end up merging clusters together. All right, one more try. Let's tweak the algorithm to get consistency back. Instead of a fixed threshold or a ratio distance threshold, we can recompute the threshold to be whatever value is needed to ensure that there are k clusters for some selected k. This approach has scale invariance. That is, if we zoom in or zoom out on the points, we're always making the comparison based on the distances needed to ensure that there are k clusters. And it will always be the same k clusters when we scale things uniformly. This algorithm also exhibits consistency. Making the points within a cluster closer will not change which k clusters are found. Neither will making the clusters further apart change which k clusters are found. So the same clustering will result from contracting points in a cluster and expanding the clusters themselves. However, this approach does not exhibit richness because it will always return k clusters. For richness to hold, an algorithm has to be able to produce different numbers of clusters. Trying to get all three desirable properties at once feels a little like whack-a-mole. We looked at three sensible algorithms. All of them are variations of a standard hierarchical clustering method called single linkage clustering, which dates back to the 1950s. They vary only in the rule they use to stop merging clusters. scikit-learn provides an implementation of single linkage clustering as part of a broader clustering package called sklearn.cluster.agglomerative clustering. Unfortunately, none of the single linkage clustering variations could simultaneously capture all three desirable clustering properties. Each time we modified the stopping rule to cover a property the previous version lacked, it lost some other property. As it turns out, this problem is not just caused by a lack of imagination. In 2002, Kleinberg showed that no clustering algorithm can simultaneously provide all three properties. His impossibility theorem shows that the three properties, in fact, are not fully compatible. An algorithm can have any two of the properties, but not all three at the same time. Alex Williams provided a lovely visual proof of Kleinberg's theorem. The property of richness means that we can arrange 5 points in two different ways. In one case, each point is in its own cluster, while in the other case, some other clustering is created. Now, the property of scale invariance says we can expand the second arrangement of points without changing the clustering. So let's expand the distances until the closest 2 points are as far apart as the 2 closest points in the first arrangement. The property of consistency says we can shift around the first arrangement to match the second arrangement without changing the clustering. That's because all the between cluster distances are increasing. But we've reached a conflict. Following the constraints dictated by the three properties has led us to an impossible requirement that the same arrangement of points must be assigned 2 different clusterings. It's a proof by contradiction, and the consequence is that no clustering algorithm can obey all 3 properties. The impossibility theorem suggests that no one clustering algorithm can be all things to all people. There's never going to be a single best algorithm for all clustering problems. And the impossibility theorem also licenses us to use algorithms that relax one or more desirable properties. In particular, let's look at an algorithm that lacks richness. We have to tell it in advance how many clusters to produce. The setting is that our algorithm will be given a set of points along with the ability to compute distances between any pair of points. We choose k, the desired number of clusters. Let's pick k equals 2 in this case. Next, the algorithm searches for a set of k centers and an assignment of data points to these centers. Its goal is to minimize the total squared distance between data points and their respective centers. The assignment to centers defines the clustering. We have two of the three elements necessary to define a machine learning algorithm. We have a representational space, which consists of k centers and an assignment of the data to centers. We have a loss function, which is the total squared distances from the points to their respective centers. The last piece we need to define is the optimizer. Unfortunately, optimizing this loss perfectly in all cases is unlikely to be tractable. The problem is in a class known as NP-complete, members of which have resisted efficient exact solutions since even before the class was first explicitly identified in the 1970s. Fortunately, there's a simple and elegant algorithm called k-means that is guaranteed to find a local optimum of the loss function in finite time. K-means is spiritually similar to k-clusters in that they both partition the points into k categories. One difference between the algorithms is that k-means is stochastic, so it's not guaranteed to find precisely the same answers each time it's run. K-means also favors compact groups. Remember that the mean is a measure of central tendency, whereas k-clusters can produce long chains as it merges nearby points together. Here's how k-means goes. The optimizer starts off with center locations and assignments of data to the centers. It then alternates between two steps. Both steps are simple, and both are guaranteed to decrease the loss when they produce any change at all. The first step is to reassign the data points to centers. Specifically, each data point is assigned to its closest center. Either the data point is already assigned to its closest center, in which case we're at a local minimum of the loss function, or some data point is moved to a center closer to it than the one that it was currently assigned to. That reassignment must decrease the loss, which is the sum of the squares of the distances from the data points to their centers. Minimizing the distance also minimizes the square distance because squaring two numbers does not change their relative ordering. In fact, of all the reassignments of data points to centers, assigning each data point to its closest center decreases the loss the most. The second step is to recompute the centers for each cluster. Specifically, each center is moved to the mean of the data points it is assigned to. That's why the algorithm is called k-means. Either the center is already assigned to the mean of its associated data points, in which case we're at a local minimum of the loss function, or some center is moved. Such a move decreases the loss the most over all center relocations. Let's simplify to just one dimension and consider how you'd minimize the square distance between a center and a set of data points in that one dimension. Any place we put the center on the number line creates a set of squared distances to the data points. That means that the amount of loss due to each data point increases quadratically with the distance between the center and the data point. The sum of those squared distances moves around smoothly and also quadratically. To find the center that minimizes this quantity, we can use a little differential calculus. Thanks again, calculus. For any choice of center C, we're summing up the squared distances between C and each data point to get the loss for C. Calculus tells us that the minimum of this function is found when the derivative is 0. That's the value of C where the loss is in balance. It's made worse by moving C in either direction. The derivative, L prime, is found by taking the derivative of each of the terms in the sum. Setting this quantity to 0 and solving for C gives us the sum of the data points divided by the number of data points. That is, it's the average or the mean. The mean is what we get in one dimension, but the choice of value for the center in each dimension is independent of the choice of the other dimensions. So we can minimize loss by finding the mean value of the data points in each dimension separately. No other selection of center improves the loss more than that. Okay, each time we reassign the data points, the centers might need to move. Each time we move the centers, the data points might need to be reassigned. But since the loss improves each time we take either of these steps, and since the number of ways of assigning data points to centers is finite, we can only repeat these steps a finite number of times before no further improvements are possible. To solidify this concept, let's build up an implementation of k-means. The algorithm is available in the scikit-learn library, but the steps are simple enough that we can build our own to see what it looks like. The first subroutine we need is one that takes the dataset and a set of k-centers and assigns each item in the dataset to its closest center. We set n, the number of data points, d, the dimensionality of the data points, and k, the number of centers. Next, we need to compute the squared distance between each center and each data point. By reshaping the data to be 1 by n by d and the centers to be k by 1 by d, that signals to NumPy that when it subtracts these two arrays, it creates an array of shape k by n by d. That is, it computes all combinations of the k centers and the n data points for each of the d dimensions. We assign those differences to res. Squaring each of the differences, then summing along dimension 2, that's the components of the vectors, produces the sum of squared distances, which is the square distance between the centers and the data points. The resulting array is of shape k by n. Now we want to know which center has the smallest squared distance for each data point. argmin produces the index of an array with the smallest value along the given dimension. Here we're using dimension 0, which varies over the k-centers. Center IDs is now an array with one integer for each data point that indicates which of the centers is closest. In addition to returning these center IDs, we also calculate and return the current loss, which is the min squared distance summed over all data points. The meat of the subroutine is 3 assignment statements, which could be chained together in a single line. That's one of the beautiful things about NumPy. It lets you execute powerful operations over entire arrays without writing loops. In exchange, NumPy expects us to be very careful to keep track of what the different dimensions represent in our array. The second subroutine we need for implementing k-means is one that takes the data and the center IDs and computes the centers by averaging all the data points with the same ID. After extracting the number of data points and dimension, we initialize the array of center locations to a k by d array of all zeros. This time I didn't see a way to avoid a loop, so for each of the cluster ID values from 0 to k, we do the following operations. First, form a smaller array consisting of all the data points with the current center ID. Call that array cols. To be robust, let's make sure cols isn't empty, its length isn't 0. That can happen if there's a center that has been elbowed out of the running by the other centers being closer to all of the data points. If it is, that means our center is out of the action, and we should probably pick a different location for it. We simply choose one of the data points at random to be this new location. As a quick aside, notice that reassigning the center location in that way cannot increase the loss, so our earlier analysis of the algorithm's convergence is still valid. Otherwise, there are data points close to the center, and we want to move that center to the mean of the closest points. NumPy's mean method computes the average of an array along any given dimension. Here we choose dimension 0, which corresponds to the different data points. So mean produces a component-wise average of all the data points with cluster ID equal to I. After completing the loop, we return the newly computed centers. With these two subroutines in hand, k-means can be described very simply. We initialize the k-centers by selecting random data points. This choice is quite sensible because it ensures that the centers are in the right neighborhood. Choosing random d-dimensional points is another option, but it runs the risk of having all the random centers quite far from the starting place of the data. We now loop until the loss stops changing. If the old loss is different from the new loss, we use assign data to assign each data point to its closest cluster. Then we use compute means to move the centers to the means of the points assigned to them. And that's it. Repeat until the loss stops changing. Here's what we get when we run k-means with 10 clusters on some image data. Here, the data are a collection of grayscale images of handwritten digits known as MNIST. The centers are averages of these images, so we can plot them as images. K-means does a very good job of categorizing the digits just based on their appearance. K-means isn't using the official labels, just the raw data. But we can see that k-means identifies a 0-looking cluster, a 9-looking cluster, a 1-looking cluster, another 9-looking cluster, another 9-looking cluster, 8, 3, 2, 6, and another 1. Okay, no 5, no 4. although one of the 9s looks pretty 4-like. Okay, so it does not perfectly assign images to digit categories. In part, it's discovering that 5s and 8s are more similar to each other than slanty 1s are from up and down 1s. Even though there are 10 digits, there are more than 10 clusters in the data. Nevertheless, we can use this clustering to label the training data following the semi-supervised approach described earlier. For each cluster discovered from analyzing the training data, we pick one of the data points in that cluster at random and request its label. The labels we get for these clusters are 0, 7, 1, 9, 4, 5, 3, 2, 6, and 1. Next, for each testing image, we find its closest cluster and predict its label as the label of the associated cluster. The resulting accuracy is 50%. Okay, not great, but way better than chance. Since there's 10 categories, chance performance would be 10%. By way of comparison, nearest neighbor classification on this data using 10 labeled examples results in a lower accuracy of 45%. We can improve things significantly by letting k-means identify more clusters and labeling each cluster. I found that k equals 50 clusters allowed semi-supervised k-means to achieve an accuracy of 80%. K nearest neighbors with 50 labeled examples also improves to 60% accuracy. It's not improving as much as k-means does. The specific flavor of semi-supervised learning I just described uses the clustering to request labels for specific points. Instead of passively accepting labels on arbitrary points that might be in the same cluster, it actively requests labels that will be as informative as possible based on the unsupervised analysis. Algorithms that can request their own labels are called active learning algorithms. So our k-means approach is an active, semi-supervised learning algorithm. Semi-supervised learning, especially when enhanced by active requests for informative labels, gives us an important way to make the most of a small set of labeled examples. For the most part, active learning algorithms are a special case of semi-supervised learning algorithms because active learning can select among the unlabeled examples for examples whose labels would accelerate the semi-supervised learning process. K-means is used standalone in unsupervised settings too. In business analytics, it is sometimes helpful to organize a business's customer base into segments that might have different interests, preferences, or needs. K-means can provide an analysis of customer descriptions that groups similar customers together. A streaming service might discover that some customers are most interested in romantic comedies and others in murder mysteries, and tailor the service differently for the two groups. K-means can be useful in image analysis to break up the pixels in an image into regions, automatically splitting foreground objects from background objects. Back in the day, when computer displays could only show a small number of colors at any one time, a version of k-means was used called vector quantization. The quanta, in this case, were the 16 or 32 or 256 representative colors that were used to replace all the millions of colors that might be in the original image. For an ocean scene, it might use the 256 colors to capture subtle shading distinctions amongst blues and greens. For a crowd scene, it might allocate a much broader palette. This idea is still used as a way of compressing an image so that it can be represented more compactly without losing the most important visual details. Semi-supervised learning strives to obtain good performance on a dataset while reducing the need for labeled data. Another well-known approach to this problem, called transfer learning, is to leverage statistical insights gained from doing supervised learning on related problems. This approach is used by experimental psychologists to quickly train image recognition neural networks to analyze behavior of mice in their experiments. They start with a pre-trained network known as VGG16 and can quickly teach it to recognize specific mouse behaviors for automatically gathering statistics of the reactions of the mice to different stimuli. Transfer learning is now a tool for automating data collection for scientists, providing the same kind of amplification of their capabilities that statistical methods like t-tests provide for analyzing statistics. Of course, there's no free lunch. We still need millions of labeled examples to train the VGG16 network. But transfer learning allows the cost of obtaining those labeled examples to be amortized over a set of visual recognition tasks. To some degree, it's a matter of luck whether transfer learning or semi-supervised learning via unsupervised clustering work in any given problem. That is, the representation learned for one task or the clustering produced might be a good match for other tasks, but nothing in the learning process is specifically trying to make the representations relevant to other problems. Another approach to learning works by training on multiple tasks at the same time, so there's an opportunity for each solution to be explicitly tailored to help the others. This general category of approach is called multitask learning. One instantiation of multitask learning is a neural network with a single input and different outputs for each task, where the branches of the network splitting into the different outputs are known as heads, kind of like a hydra. The multi-headed learning architecture makes the most sense when all of the tasks can be applied to the same inputs. For example, if the input is an image, there might be one task head identifying the category of the objects in the image, and a separate task head specifying its position in the image. Two tasks, same input. Some possible sharing of internal processing that benefits both. How to make effective use of data with only limited labels is a core problem in machine learning. Even though massive amounts of labeled data are easier to come by than ever before, there is always a long tail of new problems for which labeling of data is impractical. As such, many learning variants have been created to address different situations in which other knowledge can be leveraged to reduce the need for labels. Whenever it's cheap to gather large amounts of unlabeled data, but obtaining labels is expensive, semi-supervised learning applies. Semi-supervised learning can be augmented with active learning if it can be made possible to request labels for specific informative examples. Or, the large amounts of data that have been used to train related problems can be leveraged to perform transfer learning. And for related problems that share the same input space, multitask learning can be used to magnify existing labeled data when it is available. All of these approaches amplify traditional supervised learning methods. Semi-supervised methods are essential tools that are helping people apply machine learning in all sorts of cases where a lack of labeled data could otherwise make machine learning impossible.